All right, so we left off looking at the model requirements that we walked through here, these various requirements for EMT models. And yeah, the next thing we're going to look at is some of the performance tests that we typically run on these models as part of the model intake process. So I'll be looking at the electronics model requirements as a reference. They are based on the what success criteria is generally based off 2800 requirements, and as I mentioned, the tests are fairly well aligned with what's in 2800.2 right now. And before we even start looking at the test, I'll just say that for we have to put some number in for the grid representation and in our model testing. And we generally recommend using a moderately weak number like SCR 2.5 for most tests, with the footnote that you can adjust this SCR to reflect the N-1 interconnection SCR of the actual plant where it's going. Now, keep in mind all the discussion that we had about SCR and system strength yesterday, that it can be hard to define and that you need to take into consideration other resources when you're looking at this short circuit ratio number. And so, the note here, if the system strength is not known, using a relatively low SCR in the test system, such as 2.5, may be helpful to avoid issues during study phases. So this is, if you don't know what the strength will be in the system, if you don't have that sort of information, or if the system strength is really hard to define, then we would recommend just using a relatively low short circuit ratio, like 2.5 or 3 for your testing.
What about the XR ratio? Do you have a SL 5 or 6? Is there like something come back those numbers, or just random sort in there?
I mean, I wouldn't say they're random. I mean, you can, if you have a power flow case, you can poke around pretty easily in most systems and get a feel for the X by R ratios at various voltage levels. And they'll vary, but at like 138 kV or so, I would say 5 to 6 is pretty reasonable. As you go up in connection level, you might get some higher numbers. If you go down to 69 kV, you'll get some maybe a little bit lower numbers.
Yes, I remember back in, not when, but it was before all those renewable chaos, there was some definition on if you're a weak system or strong system by XR ratio. Back then, I think the number was 10 or something. I don't know, gradually they start through all kinds of numbers there. I just wondering if there's a study or whatever behind that, or just like, by 6 is common, but not actually for weak, right?
Right. Yeah, I mean, it doesn't necessarily mean you're in a weak or strong system with your X by R ratios. It doesn't necessarily say a lot about the strength of the system, I would say. I would say that, weaker connection points typically, like, for example, if you have a plant that's connected on 138 kV and you lose one of the connections out of your point of interconnection, now the power is probably going to be diverted more into the subtransmission. Probably your X by R ratios are going to go down.
I feel like isn't it like if the XR ratio is the smaller it be, that means the P and the Q is coupled more and it make it weaker?
So just having more coupling doesn't really say anything about the strength of the system. It may that can definitely like pose a challenge to the inverter controls if the X by R ratio is like really low. Perhaps there'll be some special tuning needed for that plant.
Yeah. Again, my question, right? Back to that, isn't make it a smaller, make it worse? The test is say 2.5 and then XR ratio 3, something like that. It would just
it's a good question. I mean, it's not. I wouldn't necessarily that smaller X by R is always worse. Like you also have more damping in the system. We have more resistance, so it's hard to make those kinds of conclusions, I would say. But I would say for weak system, short circuit ratio is much, the sensitive factor is for sure short circuit ratio. Yeah. And the utility should be able to get you, it's much more easy to define X by R ratio, I would say, compared to system strength. So that should be a much easier number to get from the utility for a given connection point, in my experience.
So one pencil using 5, the other one turning to 6.
Well, yeah, that's the ballpark of what I normally see in cases, but yeah, it's a good question.
If you have a real test, again, not for this, because there's probably design evaluations before you have a connection, but if you have a real test with real data, like a mod 26 reactive power test, you can use that test to calculate your X over R ratio and grid impedance as well, right? Because you can just take the magnitude of the Q response, the magnitude of the voltage deviation, and that gives you X over R and impedance. Like I said, you can do the same thing in a load flow as well. But doing the real test is also really useful for those who are going to do this again post commissioning.
Okay, so yeah, we'll walk through some of the tests here, and we might take some tangents here, but first one here is just real basic flat run. Can you get the plant to initialize to the steady state within whatever your criteria is? We would say 5 seconds is a reasonable target, but this is tool dependent. Some tools will have some inbuilt features which may enable a much faster initialization than 5 seconds here, but I think on PSCAD at least, mostly we're looking at 5 seconds as a target. And you can do your various power levels here. This is and your various active and reactive power levels here. If you're doing this on a hybrid plant, you'll want to test basically all of the initial conditions that you want to run for your various other tests. Useful to just do an initialization test, of course, just to make sure your logic is working properly and that the plant is coming up to the appropriate levels in the right time frame. So okay, so looking at low voltage ride-through tests, and I guess maybe before I do that one, this note about SCR, this is, I think it should be your objective in the design evaluation or the performance testing to keep the system strength in this region. Like whatever if you know the interconnection strength, then try to run the tests at that interconnection strength. If you don't know it, use 2.5 and run as many tests as you can at that system strength. There's some tests which are much easier to do, let's say, using a much higher short circuit ratio, and we will talk about that. But as sort of a guiding principle for these tests, I would say try to use the actual grid strength wherever possible. And it'll make a bit of sense with this example here. So looking at low voltage ride-through test specifically, we have in 2000, we have pretty small for you, but we have these tables of ride-through requirements. So, as you know, for a certain voltage level, we need to ride through for a certain amount of time. And the question is how to, we want to exercise the controls of the plant to see whether it's going to ride through these voltage levels, to see whether it's compliant, basically. So there's different ways to do this, right? So one way is to take your IBR and set the system strength really high, and then on your voltage source, just play in the exact voltage profile here. So you can play in the exact extents of the curve. And this method is not great because, well, it's good in some way and good in not another. Not good because you have no system strength here. Your system strength is it's really high. It's unrealistically high here. The benefit of that is that you can have very tight control over the POI voltage here. But the downside is that this test, you're now testing it in a very strong system that's not realistic of the actual connection point at this point. So there's different ways of doing this. Now, if you try playing in, if you actually put in your SCR of 2.5 in this test, so if I actually go ahead and put in some impedance here. Inductance here that represents my SCR of 2.5, let's say. Now I have very tight control at my source end, but not at the IBR end of this little test system, right? And then this IBR will be able to move that voltage around a lot, potentially, and make the POI voltage not be matching with these levels anymore. So what you can do instead is you can use a voltage divider effectively. So let's say for a voltage level of 0.5, you can take your fault impedance and just match it to your source impedance. And then you just get a voltage division across this impedance, and your voltage IBR will be roughly 0.5 per unit when these two are matching. 0.5 is a bit of a unique one because you also get even like the current splits here nicely across the two impedances, the two impedance branches here. If you don't have, like, for some other fault impedances, it won't split so nicely, and you might get some other voltage levels here. But so far this is one aspect I think that could be expanded a fair bit, but we are basically just testing zero bolted faults, and this configuration with 0.5 per unit is all that we're kind of testing for now. We're testing it for a wide range of faults and a wide range of initial conditions at the plant, let's say. So here you can see for the balance test, it's 6 tests here. The first 3 are for bolted fault of 160 milliseconds with 3 different power levels here, 0, Qmin, Qmax. Next 3 are a longer test, 2.5 seconds, with the fault impedance equal to the source impedance, and then the same sort of dispatch assumptions. And the reason we're going 2.5 seconds here is because in this table 11, you can see for voltage below 0.7, the minimum ride-through time is 2.5 seconds there. So we're testing that to the full range of what's allowable in the standard there. And for unbalanced faults, we're also trying a series of unbalanced faults as well. So 2-phase to ground and single-phase to ground tests. For those ones, we're just doing bolted, just 160 millisecond bolted faults. And yeah, we typically see IBRs don't really have a problem with these balanced faults in most cases. You're probably more likely to run into issues with these unbalanced faults. It's very common to see tripping issues either during the fault or at fault clearing, related to them basically not having very good. They basically are injecting reactive power into healthy phases of voltage and resulting in over voltages and tripping due to those unbalanced fault conditions. So these are 2 different ways that you can go about testing these low voltage ride-through tests here. We would recommend, option 2 here wherever possible, again, to maintain the strength of the correct system strength. There's also some requirements for the response during low voltage in 2800, which we can look at. Before I go there, actually, success criteria here is an important question, right? In our requirements, we are asking the plant to ride through these tests. So you want to see active power come back after the fault, and it should come back. I think the criteria is 90% within a second in 2800, and you don't want to see it. You don't want to see it in momentary cessation after the fault either. You want to see it basically start injecting as soon as possible. Yeah.
So do you test this like for a best case? You have to test for both Emac and Qmin, or just
For a battery?
for a BESS?
That's, yeah. Yeah, so that's a good question, what kind of conditions we need to test for a BES plant. I would say here we're saying Pmax. I think yeah, for a battery, you would definitely want to test it at multiple operating conditions. So it gets more complicated for a hybrid plant yet. I would usually say like 2 or 3 different operating conditions for a hybrid plant, and possibly more, depending on what your appetite is for for running a lot of simulations, basically. But yeah, I've definitely seen different responses where, let's say, like if you have a hybrid plant and the PV is at Pmax, and it's not necessarily the worst case to have the battery at Pmax as well. Maybe full charging might be the worst scenario for the battery as well. So there might be a variety of different dispatches you look at for a hybrid plant or for a battery. Good point. Yeah, and the whole testing procedure gets, like, the complexity goes up a fair bit when you're looking at multiple resources. Mostly the examples I'm showing here for a single resource, but the principles still apply. So low voltage ride through, response during low voltage. So what should the actual like current outputs look at? So here in 2800, we have requirements on how fast that current needs to come up, the settling time and step response time and the settling band. So this can be, for a balanced scenario, this is fairly easy to look at. You just look at the current out of the device and see how fast it's coming up. For unbalanced conditions, it can be quite a bit more complicated, let's say. But yeah, mostly we're here looking at in for unbalanced, you maybe need to look at only the positive sequence, and you can't maybe just look at RMS and things like that. So it can get more tricky there. The high voltage ride through is, so this one's a little bit take into consideration what I said before, that you want to maintain the system strength wherever possible for these tests. It's a little bit tricky to perform this high voltage test with the system strength actually modeled, because we don't have the ability to do that voltage divider mechanism that I talked about before. And the only way to sort of like impose that with passive elements is to actually like switch in like a capacitor bank or something at the POI to sort of make that voltage rise happen. You can either do that or you can play in a voltage, right? So the capacitor switching thing has some, is problematic in other ways, I guess you could say. You might need to switch in a rather large capacitor bank, depending how strong the system is, to move the voltage, and then you have a transient that's caused by the capacitor coming in and out. So that one we would generally recommend doing some sort of play-in for it. That in this example where we have no source impedance here, so it is an infinite bus for this test. Now there's other ways you could do that as well. You can put in your source impedance, and maybe you can just try a whole bunch of different voltage levels and do a sort of an iterative process until you find a certain source side voltage that gets you the POI voltage that you're interested in. And you can, if you know the HVRT parameters and you know the impedances of the plant and the deadbands, you could maybe also go through a theoretical calculation of how to set that source side impedance, but it's quite complicated. But it's up to you what sort of complexity, I guess, you want to go to for these tests. But typically for this high voltage ride through test, at least in the electronics model requirements, we suggest just using an infinite bus plane for this specific one. And for this one, we're looking at 1.2 per unit for 1 second is what we test. And this one can be, I believe we test this at, Qmax as well. So it can be a challenging one as well for the plants when you are already at Qmax and then you step up the voltage to 1.2. You're seeing might see a fairly large overvoltage at the inverter terminals for this test. Now, the steady state voltage response test is mostly looking at these performance requirements from 2100 where, where you apply a steady state change in voltage and see how fast the plant can respond. This can be a fairly interesting test. So in 2100, there's a performance target of 200 milliseconds, which is honestly, it's quite fast, and there's not a lot of plants that are meeting this, I think, today on the system. There's quite a bit of delays involved in these sort of closed loop plant level voltage response tests. You have to measure that there's a voltage change, and you have to process that through the plant controller, and and then spit out a new command to the inverter. There might be some Modbus communication between the inverter and the plant controller, which will slow things down as well. So that sort of like round trip can be significantly longer than 200 milliseconds. So this is one that, I don't know, maybe it'll get revisited, but this is, yeah, it's pretty hard to meet this one, I would say. Not hard, I'd say, but like the plant has to be designed well ahead of time to meet this requirement, and everybody has to kind of be on board. Especially, the PPC vendor has to be quite informed of this requirement, and be designing the sort of setup of the plant with it in mind. It doesn't really give in the standard. It doesn't give a response time requirement here. And it says, step response time may be typically between 1 second and 30 seconds. Is kind of all the advice it gives there. We recommend step response time less than 10 seconds in our model requirements. And this one, you do need to be, just a little bit aware of tuning this very aggressively. We've seen it a number of times where if you test a model that has a plant controller that doesn't have delays modeled, for example, and you tune it to give a fast response time in, let's say you do the tuning in a relatively strong grid, say a CR of 10 or something like that, in your model at least. When you go and take that into the field, and now you have your actual communication delays that maybe were missed in the model, then during commissioning, it'll start to oscillate quite quickly on you. So something to be aware of. You want to, if you do your tuning for a low system strength and you include your delays inside your plant controller model, then you should be pretty safe, assuming your models are accurate. But there are some missteps you could take here. Active power step test. This is not in. There's no time requirement for this test in IEEE 2800, but for this test, we just take the power reference and we change it. We vary it, and we see how fast the plant responds. There's no time requirement for this one in 2800. And our success criteria is just that the plant should respond appropriately. So it's kind of discretion there. Frequency response test. Here we are looking at over voltage over frequency and under frequency. And this one we are looking at ride through as well as specific parameters in terms of the reaction time, the rise time, and the settling time. So we're kind of using this test to check the response time as well as the ride through of the plant. And for this one, you just need to be careful to not sort of like step this voltage. You do have, in 2800, there's a maximum rate of change of frequency that's defined as 5 hertz per second. So what we do for this test is we ramp it up from 60 to these values at 5 hertz per second. So we don't exceed that 5 hertz per second ramp. Phase angle step here. So in 2800 we have a requirement that you have to be able to ride through phase angle steps of up to 25 degrees. This is not fault related. This is sort of tested without a fault in this example here. And I think that's there's a lot of discussion about this in various forms, but generally we do this test without a fault, and we just take the system angle and we can apply a step change to it, a 25-degree in this case, and we try that at different power levels. And this really exercises the inverter's ability to align with the new system angle, similar to what I was showing in the phasor diagram earlier on. Has to be able to very quickly take that internal phasor and rotate it to match the new system angle. And you might see some interesting transients while you're doing this. In this figure here, you can see small, but yeah, when we apply that phase angle jump, there's a fair bit of wiggling happening here on the active and reactive power, as the PLL and the inverter current control is working quite hard to maintain synchronism and not exceed current limits. Typically for a grid following inverter, we wouldn't really expect to see like a massive response out of it if it's well tuned. For this type of test, in a lot of cases, you're going to apply this and you just see like a pretty small blip if it's well tuned to be able to handle this sort of condition. When you apply this on a grid forming inverter, you will see a significantly different response, because that mechanism of maintaining very quickly shifting the internal angle it looks different for a grid forming inverter. So you would expect to see larger, specifically active power transients out of the inverter in grid forming mode, and there's a good reason for that, which we might get into yet, but for now, I would say this one isn't. I don't see a lot of inverter like EMT models tripping for this for a phase angle jump test. Mostly, if they are tripping for this, they're also tripping for some of the just fault tests that we're applying as well. So this one, I haven't seen it failing in isolation too often, maybe never. So it's heavily correlated with other ride-through performance issues if there is one. So the second last one here, this is a short circuit ratio change test. This is a very interesting test that we've had in our requirements. I think this is probably one of the first ones that we added before any of these other ones even. Just something that we're always quite interested in looking at. So what we do is we take the plant and we have it connected to our source impedance, and what we do is we vary that source impedance over time according to this figure here. And every time we step the source impedance down, we also are applying a fault, so that when we're basically mimicking a series of faults and line clearings, let's say, on the system, and but all in our simple test case, right? So this is sort of an artificial test in that we're applying like a whole bunch of faults right after each other, and maybe you run into some sort of consecutive fault ride-through limit here, but in that case, you can definitely space them out further than these 5 seconds that are shown here. But this is a very useful test to get a feel for what sort of system strength the controls are going to start having a problem with. And here you can see, things are looking pretty good. I think this is 2.5 here, this transition. And as we go lower than 2.5, I think this is maybe 2 here. We are recovering. It is not the prettiest thing in the world, and we're definitely not at 90% by 1 second anymore. But this is, SCR2 is very low. As we keep driving lower, less than 2, we just start to see these oscillations developing here, which is quite typical of weak systems. Either have some sort of mode cycling, which Alex showed yesterday, or you can have these small signal oscillations building up. And Yeah, so for your typical plant, you're definitely going to start to see some sort of issues pop up at these lower short circuit ratio levels here. And this test we do, even if we know that the plant is connecting at a higher short circuit ratio in the system, it's still useful to know what sort of limitations the model has, let's say. And maybe you start to see something at these lower short circuit ratios that maybe calls into question the accuracy of the model. And maybe you'll see, very large overcurrents, let's say, that are maybe higher than what you would expect to see based on our understanding of current limits inside of IGBTs. Maybe you'll see it act like totally flat, like give you like extremely good performance. That is, that might make you ask some questions about the accuracy of the model. Are they doing something inside the controls to make it look better than reality? Gotta be careful on that one. Maybe the performance is really good, but it could be that something is overly optimistic in how they put that model together. But yeah, so we're calling this one as an informational test. So generally, you're not going to apply like a pass fail based on this one, and mostly you're going to be looking at it just because we're interested to see how things perform in weak systems. That being said, you can still get a lot of useful information from this test. I'll say one thing that we do see once in a while is that it'll be passing all of the other tests, like even at like a short circuit ratio of like 3 or something. And then you take it into this test and then you step it from like 20 to 10 and it fails to ride through this test, which is sort of a strange situation, but it does happen sometimes when you have a fault and an angle change, which is kind of what we're doing here. You can get a different recovery dynamic than just a fault or just a phase angle step. So if you see that happen, then it's a good idea to poke a little bit at that test and probably, if you know that the connection SCR is going to be lower than the sort of stability limit that they're finding here, then that's definitely a good thing to feed back to the plant, and you might sort of ask them to fix something based on this test in that sort of special scenario. And the last one here that we typically run is a protection inclusion test. And so what we're doing here is we are stepping the voltage up by some unrealistically high number, let's say to 1.5 per unit, and we keep that for about 5 seconds. And we see how the plant responds. This is one where we're intentionally applying a voltage that the plant shouldn't be able to ride through. And the main reason we're doing that is to just verify that some protections are enabled in the model. Just to give you some confidence that, when you actually take this and run a study with it later, that you can actually, it's just that that the protections are on in the model effectively. Now, this isn't the only way to check this. Like you can check the parameters in the model and have a look at how well they correlate with other information that's been given to you, maybe about the actual equipment, etc. But this is sort of a quick test that we can do in our initial model testing to just make sure protection is there. You wouldn't believe how many models get submitted with protection disabled altogether. This is a good one. Right. Any questions on those tests so far? Yeah.
I'm just curious, did you talk, I may have missed it, did you talk about the cumulative low voltage ride through? You guys have just for the one that I think is part of the 2800?
Yeah, so the cumulative questions about cumulative low voltage ride through. For these under voltage tests, you can definitely come up with different profiles which would exercise it. Like you could apply for the 2.5 second one, maybe you apply a fault for 1 second and then wait a little while and then apply a fault again for another second. Or however you want to sort of like stage it. So you can definitely come up with different sort of envelopes of how you can come up to these sort of like total cumulative numbers. We haven't been, I don't know if that's, it hasn't been proposed in our requirements at least. I think maybe some other grids have done that. But it's something to maybe add, I think, at some point. But
It's usually not tested because it's not in the model space. And that's a limitation of these, 'cause the thing that causes issues, cumulative fault events, is thermal problems, heating up of equipment or copper circuit and stuff like that, and those aren't in any of the models. So literally, the cumulative drive-through representation is a counter. The attribute 200 is 5, and they'll say, well, the voltage is below 0.90 per unit, that's 1, 2, 3, 4, and on the 5th time, you trip offline. It's a requirement of the base standard 2000, but it's not something that's in the model space at all, even in EMT at this point. I don't think any simulation domain, unless you're doing like a bespoke, like I'm the designer of the equipment with a finite element analysis of my thermals, are going to be able to actually test it. So it's always just a counter.
and so Alex, that's the multiple faults right
Multiple-
through.
Multiple low voltage right through.
And what's the timeline? What's the time? Is it 30 seconds or is it on the minute?
Something like that. I think it's 5 and 30 seconds.
5:30. But this one is still like these 2.5, you can still spread out over some cumulative window that's different from that one, right, though? Yeah.
Yeah, I mean, in the counter may not be any, that's just if people even want to have something in there. And that was one of those instances where they never modeled it because you can't. And then 2000 came out and then people started asking, do you have this in your model? And they'd say, oh, we should do that. But the best we can do is put a counter in there. So to keep in mind that if you're trying to test it for the requirement directly, you're not going to get a meaningful answer. But if you're trying to do your own test bench, and maybe that involves multiple different depths of fault in a certain amount of time, and it's stripping offline always on the 5th fault or always on the 7th fault or whatever, that's also a good indication that maybe it's not. Maybe it's a model hard coding thing that is a problem, like Lucas mentioned earlier. It's probably just a hard coded value in there that says after blank. Good. So just a lot of times when you're doing a low voltage right through test, you don't do that many that quickly. You don't often run into it, but if you have a manufacturer with a user-defined model that has a counter in there, you may see weird trips that you aren't expecting. But again, this wouldn't be also in the generic level.
Yeah, I was thinking about it, and I think the way we was curious how it measured up first was basically a bunch of really short duration dips that had the summation of greater than the requirement over that 30-second time period. So they weren't necessarily faults; they were just infinite bus with dipped dips. And then none of them would exceed the duration where they'd be allowed to trip instantly with that dip. But then the sum of them was greater than the requirement. So it sounds like it's.
Yeah. So yeah, I think for that one, if you see a trip, it would be due to just like a counter in the model.
It's again the transient immunity. The name of the test? Then the transient immunity test, the one you are referring to?
It's multiple low voltage dips in a period of time.
Oh, okay.
Cumulative, yeah.
The thing is reclosing.
I mean, reclosing will look like that, or can look like that. I mean, the large load event. I don't know. I'm not going to say that. The large load event looked like a lot of it was 5 reclosings in a row. They probably don't have the same controls like this. They, for some reason, for their power quality requirements, that many reclosings in that short of time, they tripped offline. Probably not the same function or the counter or whatever, but there was something with that amount of rapid closing or dips that caused them to trip offline. That's the kind of spirit for why that is in the 2000. But then it's what happens when you're very ambitious with the base standard. Got to be forward looking, right? And then you end up with a case where, sure, it's great to know, but we don't, they're not in any of the models, anybody's model, EMT or otherwise. So it's a great requirement to have, be cognizant of, and put someplace maybe just to have there and tell the manufacturers. But you're not gonna be able to say, prove to me that you operate this way, because you can't.
Any other questions?
Any tests combining like LVRT event with a frequency event, just see how maybe different controls can interact, like rectifier injection with FFR, things like that.
Yeah, no, that's a really good question. So in the standard, it's doesn't really specify that, you know, I mean, I don't know how, I don't actually know how it's treated in 20 to be honest, but to the point about testing specifically, I would say if the system, if the system needs it, and if you see those types of events happening in your system, then you can definitely include those types of things in your model testing. Like specifically, from experience in Hawaii, they, you know, they had their specific sort of MQT type tests, and also they had some specific grid forming capability tests. But when we go ahead and do the studies, the system doesn't really respond like any of those, right? It's something else. It's obviously it's unique to the system, but so they sort of devised this sort of torture test where we did that. We applied a fault, and then while the fault was still on, we did sort of a recovery like this on the voltage, and then we did a phase angle jump on the voltage, and we applied our steep rock off and then a shallow rock off, and then like this. So we came up with this sort of torture test for the model, which is kind of captured what we were seeing in system studies a little bit. So it's that one. It's not like enforced. I'd say it's like an informational test, and then if we see the same thing happen in a study, let's say as the simple test, then we can say, why don't you start with fixing this simple test, and then we'll try again in the system, sort of thing. So, but it's a really good question.
2000, you're testing. If you're testing voltage, you're looking at voltage. Testing reactive power, you're only looking at reactive power, and that's where the requirements are. There are other requirements like ERCOT where it says for voltage right through, you need to maintain active power at the level plus reactive power magnitude, which is, I guess, maybe two different control systems at the same time. It's definitely a capability thing. But one of the benefits of doing things like this in EMT is that you don't have to fudge stuff like you would have to do in the PSPD. So what happens a lot of times in the PSPD, and ERCOT may have fixed it with the change of the filtering constant. But it used to be for certain sizes of plants with the system, single machine input bus, the ERCOT or other low voltage profile, or just a fast shift when you're using the single machine infinite bus and you're doing that voltage profile thing that Lucas was talking about. It's an immediate magnitude change. And in a phasor domain, that means you're probably getting a really crazy fictitious frequency, like 70 hertz, because it's by virtue of the simulation, you get a spike like that. And if that spike's longer than your filter time, then you're going to trip on frequency, or you're going to have a PFR event. So what people do is, if I'm doing a low voltage, high voltage ride-through test in the PSPD, they turn off frequency protection and they disable the PFR loop. But that's something you do in the PSPD because you have to. You shouldn't see that same type of calculation issue in the EMT. So you can feel more comfortable just running the plant or the model with the controls you expect to be in service all the time and run the tests of the EMT. And you should see, saying should, probably, you definitely will not see that in the EMT world. That's another benefit of doing it in this, in the simulation domain, because a lot of times people forget to turn the protection back on. There are a lot of models out there with, commented out frequency protection settings or plants interconnected last year with PFR loop disabled because they turned them off. You don't have to deal with that in the EMT, but to actually answer your question, I can't think of any requirements, like actual requirements anywhere. Even in Europe, I think, or even in AMO either, which AMO doesn't have it. Probably no one has it. where you're doing both at once. I don't think anyone's doing a frequency and a high local. You could. You certainly
Yeah,
could.
I mean, you'd have to ride through it, right? According to the standard, you'd have to ride through it, so. We can't. Okay, so I think we'll take a little bit of time and just look at just a basic representation of how you could test these in PSCAT or an EMT, an EMT tool. You could do this. And yeah, we'll show you like one method to do this, and you can do this as it's going to be extremely sort of tool dependent. Some tools, I think EMTP has like some of these features like baked right into the software to do this testing. There's a lot of like third-party folks who are building, I would say like add-on tools for some of the EMT tools to externalize this sort of MQT and design evaluation testing. So there's a lot of like options for like how you can do this, but I'll just sort of present sort of a bare bones approach, which can definitely be extended to more sophisticated levels. So I think I'll just open it up in the tool here. Probably easier to do that, to be honest. Okay, so again, this is the same generic PV plan model that I was showing previously. And let's have a look at this test grid block here. So before I even go into it, we can check out the parameters of the model. We have some inputs here, our test number, our base voltage, base frequency, plant MVA rating or megawatt rating, and some initialization time at which we want to apply our test. And so these are getting sent into the model. Inside the model, in terms of the electrical representation, this is side, it basically just looks like this. So this N is our external connection, and we have an infinite source behind a variable impedance here. There's R source and L source. And then below we have a fault impedance, fault R and a fault L. And then we have a fault block here. So we can send signals to control when we want to see a fault. And we can send signals to play with the grid voltage and frequency. And we can also, if we double click on this source component, we can see that we're sending a signal to shift the phase of the voltage as well. And so this is all we have in the model in terms of electrical representations. And then if we go below, we have a few different blocks. Here's just some scaling, and here is a short circuit ratio calculation block. So you can take whatever short circuit ratio you are testing and your planned megawatt, your X by R ratio, and your nominal values, and come up with a R source and an L source. And then we can use that to populate the variable resistors and inductors here. And we scroll down a little bit. We have basically just a series of sequencers that we're using. This is probably something like this exists in other platforms too, but this is PSCAT specifically. There you have these sequencer blocks, which we can very easily use to set the condition for variables quite easily. And then for a specific test, I can change the parameters that I need to for that specific test. So kind of a very flexible way to automate your testing here. So we basically take these sequencers and feed them through a channel decoder in here, and we apply a test number here, and that diverts the data stream to the right sort of variable of this output here. Don't worry too much about that. That's very much a implementation detail, and there's many ways to do this in EMT, but this is just one way that we found to be quite flexible and easy to manage a whole bunch of tests this way. So you can see these we're pulling out different sort of indexes out of this big array here, and the indexes correspond to the test number. That's really all you need to know for that side of things. So test 1 and 2 here are just flat runs. We can set our PQ to whatever we want to here. And in this case, it's actually just P that we're playing with. And so PREF is getting sent out of the component. If we go up one level, you can see PREF is coming here, and it's getting sent to actually as an input to the plant controller over here. And similarly with voltage reference over here, so we can manipulate the voltage and power reference of the plant controller. And if you wanted to try different control modes, then you can have a QREF output as well, or a power factor reference as well out of your control block. When then internally you can customize some automation to test those outputs. But for now, yeah, flat run, we set our PREF, and basically it. I guess before that, we set some initial conditions here. And this is actually a small typo here. This shouldn't say SCR3. This SGR should be getting set to what we're importing from the case, which is, oh, it's actually not, okay, it is hard-coded in. This one's actually hard-coded inside. Okay. This, most components, you should probably have this short circuit ratio as an input to the component just to make it easier. But anyways, this is a kind of a bare bones thing that we're looking at here. So flat run, under voltage test here. Again, this is just the, wait for initialization, set your fault impedance, apply a fault, wait 2.5 seconds, and then release the fault. And if you're doing the bolted scenario, same thing, except the fault impedance can stay at default, which was 0. And under voltage unbalanced, you can see 3 different faults here. We're setting different signals for the fault type. We're setting it to different things, so that's fairly straightforward there. Voltage reference step test. Waiting for initialization, setting VREF equal to 1.05. Initially it was 1. PREF, just setting PREF to 0.5. All these tests can be extended to whatever your specific requirements are that you need to test for. This is just, again, just the bare bones kind of demo. Over frequency, similar, set your frequency set point to 1.03. Somewhere there should be a ramp limit here. I'm not sure if it's in here, but you should be ramp limiting this to, or rate limiting this to 5 hertz per second, this change. Right through, again, setting your source angle from 0 to 25 degrees. Fairly straightforward. SCR step test, we are looping through this set of sequences 4 times here. Each time we are just looking at a different short circuit ratio. Initially, we start with 2.5, and then we go down to 2 and 1.5 and 1 in this example. I had different numbers shown in the figure before, but it's easy to change. Okay, so let's say we just want to test those 14 tests for now. And here we can have a look at the results of this testing for our generic model that we're working with here. I've gone ahead and ran these tests ahead of time. This is a very small case. It runs fast. It would run fast. It runs quickly, so even with a significant number of tests. But if you have a detailed model with perhaps with multiple IBRs in here, and the actual switching models or whatever, then these tests can actually take quite a bit of time to run. So that computational time can definitely be significant. So this test 1 was a just flat run, I think. So we're getting to Vmax of 100 megawatts, and you can check your Q. Should be around 0 for this test, given just for this specific system strength. Test 2 here was just PREF set to 0. So just testing that different condition. Test 3, I think we didn't define test 3. Under voltage is the next two. Balanced is the under voltage is test 4 and 5. We can look at some results for that one. Seems to be riding through okay, and as you can see, it's giving us a lot of reactive power during this test here. You can note that the voltage here is only 0.5, and the model is going into, the active power is going into momentary cessation here. This going all the way down to 0 for this model. That may or may not be acceptable. This is during the fault, so the emphasis should be on reactive power during the fault, and it is giving us reactive power, but on the active power side, it is going down to 0. I'd say some regions might have a requirement for what level of active power you maybe need to maintain during the fault. I would say they might say, try to maintain your pre-fault active current or something like that. But they should definitely be, in most scenarios, you should be trying to emphasize reactive power during the fault. There's some exceptions to that, but most of the time that's what we want to see. You can see there's a bit of an interesting blip here at the beginning as we apply the faults. I think this is due to the way the active power blocking is sort of doesn't latch for a little while, or maybe it triggers and then it untriggers and then it latches again. So there's something kind of interesting transient happening there. And test 5 is just a bolted 3-phase fault for 160 milliseconds, so no problem there in this case. You can see some reactive power, some somewhat interesting reactive power outputs out of the plant after the test here. As it, the reactive power is sort of stepping up and stepping down, and definitely has some movements here. So this, I think in this model, it's not, it's maybe winding up a bit during the fault, I would imagine. Maybe the plant controller is winding up a bit, or something like that. So there's, it doesn't seem to be causing a problem on the grid, but you can see that there is some overvoltage that is happening at full clearing due to that injection of reactive power after the fault. So this is something that you definitely can see issues with in these tests as the coming out of the fault. During the fault, the phase lock loop, it doesn't have there's no voltage to measure, right? So it's kind of frozen to a degree. And when it comes out of the fault, it's going to have to resync to the grid again in some respects. And while it's resyncing, you might see current that is maybe not what the grid needs, like, let's say. So active power might go negative briefly. Reactive power might go sharply positive as that angle is perhaps not aligned with the system angle yet. So that's, especially in a weak system, that's often where you'll see some interesting transients, which may cause the plant to trip, depending on the system condition. But in this case, there's some transient there, but it is riding through. Test 6 here is let's check. Is a single underground fault, and then I think test 7 is a line to line, and test 8 is a 3-line to ground. So you can always, in EMT, you can always have a look at the instantaneous voltage here is sometimes interesting, and you can see, for this single underground fault, you can actually see the voltage on that faulted phase has gone all the way to 0. And there's definitely some oscillations happening during the fault here. Seems like this generic controller may not be dealing with this system unbalance very well, and maybe causing some oscillations during the fault. And that's something that you do see in real models as well. If they're you know, not tuned or not designed to handle that situation. It may or may not be a problem during the fault, right? It's, you know, after the fault, it might recover very quickly and not cause any issues. But yeah, I don't know. We definitely would prefer to see a straight line here, obviously, but it may or not be something that you're gonna you know, put up a big fight about, depending on the circumstance. 7 is a, what did we say? It was a 2-line to ground, I think.
Can you go back to the previous one?
Yep.
Would you consider that right after the fault, those oscillations on the QI problematic?
These fluctuations here?
Like the before that, like those high frequency one.
Oh, this little
A little
one?
bit before, yeah, even before the,
These
yeah,
ones?
yeah, those.
During the fault, yeah. Not necessarily, I guess. Like we would try to avoid them, I think, if possible, and we might mark them in our model quality testing. But I wouldn't necessarily fail a plant on this in this context. If there was a system study done, then this might be a good hint to look closely at this specific fault type, let's say in a system study, and see whether it does this and see whether it causes any problems in a system study.
Before, even it's single machine, even it's all, it seems like it's been in and out certain control.
It could be, yeah. Yeah. And you could probably argue that it doesn't meet the 2100 requirement for fault current that I mentioned before. And in terms of the settling time and the settling band and the response time, that's probably a valid reason to get this behavior corrected as well. But yeah, I would probably make a note of it and look at it in system study if you're planning on doing one. If you're not doing a system study and this is all your only opportunity to look at it, then I would probably get it fixed if you can. Okay, this is test 7 here is fault type 4. Let me just double check what this is. This code's memorized, but I don't. There's lots of good help options in whatever EMT software you're using. There'll be lots of good documentation baked into the tool for all kinds of stuff. And for this one here, you can see I'm looking at, like if I feed it a number 8, that's a line to line fault. And you can have a look here. The voltage is here. The 2-line, the 8, 7. Sorry, test 7 was line to ground. Test 8 was the 2-line to ground. Yeah, so this is the line to line scenario here. And it is riding through and behaving a little bit, you know, it's basically, if you look at the current, the basic current has gone effectively to 0 on this one. So it has basically gone into full momentary cessation. So that's not great. Probably we would flag this one and say you're not providing any fault current for this test. So that's, you know, that's something that we would probably call out for this one. This test 9 is that's the overvoltage test. And in this case, the plant is actually tripping for this overvoltage test. So you can see the current does not come back after active power does not come back. We can go into these models and try and diagnose what the cause was for the trip. So here, you can click in and I can go have a look at some of these trip flags, and these will look different from model to model, like very different. Whether, this information may not be exposed in a lot of models, you might get absolutely no insight into why the model is doing what it's doing in terms of the outputs that it's giving you. But there's a lot of models that have, they'll have two things usually that they'll tell you. They'll tell you if they're in a ride-through mode, like if their LVRT mechanism is active at that time. Or they'll often tell you, if they trip, which element tripped, or what sort of like error code was thrown by the inverter. So this case here, I can see the one that, there's a few things that come up, but the one that comes at first here is over voltage 1 setting. So we could go and have a look at the protection settings if we want to, and verify that this all makes sense, basically. And so threshold 1 is 1.2 per unit and 160 milliseconds. So it's so this is definitely the one that's tripping the plant. This is too low of a threshold for this example. In terms of like, how does one fix this, right? So if the plant would be pulling down on reactive, it's actually doing something very strange here. I guess the POI current is going up. That could be just due to the filters on the plant, as we have some capacitors in the filters. So that could be why. But really, we would want the plant to be probably bucking its reactive power, and so absorbing from the system, and thereby lowering its terminal voltage, and then you could get under that 1.2 threshold, and be able to ride through this test. If you saw this in a study, I don't know, maybe 1.2 per unit, 160 milliseconds, that might be quite reasonable for the limitations of equipment. So you definitely wouldn't want to like just raise the number and like not tell anybody, obviously. If you have a suspicion that the ride-through setting is much more restrictive than what it maybe should be, then you can maybe check with whoever you got the model from on how it was set, why it was set to this number. If they tell you that's the equipment capability, then that's all you got. If they say, oh, we set it on, based on like a PRC24 ride-through curve or something like that, then you should probably, see whether you can get that value increased to the capability of the equipment, so that you could avoid the trip. So there's two different sort of ways you could possibly fix this if you ran into this in practice. Okay. Test 10 here is the, I think this is just the VREF step test. So you can see we're applying a voltage reference step at 5 seconds, I believe. And there is some communication delay that's baked into this model. So you can see it doesn't really do anything until 5.2 seconds. So it's just barely meeting that 200 milliseconds reaction time requirement that's in 2800. But I'll note this is for a voltage reference step test. Now, if you apply a voltage change in the system, then you're going to have the additional measurement delays as well in the closed loop response. So you would expect this to get actually a little bit slower if you actually applied a voltage reference or a system voltage change. And you can see in the response here that the reactive power is not the prettiest thing in the world. This is a pretty weak system. We're looking at a CR, I think, of 2.5 or 3. And it's certainly coming up quickly, but we do have some overshoot, and there's, we're coming up and down here a little bit. And this sort of like boxcar shape is like very common to see, I would say, when you're looking at, the weak system voltage response in a weak system. It's not abnormal to see something like that. And this is, due to plant controller delays and cycling time and sampling times and things like that. And again, this is a generic model, so I put these in here on purpose, but I've seen this come out of real plant controller models, things that look very similar to this. Test 10 was just a power reference step. So yep, that's coming down nicely, no problem. Test 12 here. Test 12, 13, 14. Check. 12 was over frequency, 13 was phase jump, and 14 is SCR. Okay. So for an over frequency, we are, well, the frequency isn't plotted here, but it's riding through the event. I don't think we actually increase the voltage back or the frequency back. So the frequency goes up and the plant controller is doing the right thing here and reducing the active power commands to the PV inverter. So that's why we're seeing this this active power go down. So this looks okay, and it's riding through. It's not tripping. 13 was the phase jump. Thing kind of interesting happens here with the active power. I'm not totally sure why it's doing this. I think it may be actually reading that that phase jump as a over frequency, a brief over frequency. So what Alex was talking about actually does come into play in EMT as well to some degree. So if you look at the way that I've set up the frequency measurement here for a plant controller, it's reading that through a phase lock loop on the voltage, based off the voltage. And when we increase the angle on the voltage to the PLL, that looks like a brief over frequency, basically. And the plant controller, if it doesn't have appropriate filtering, let's say, in place, it can definitely respond to that, which we can see in the commands here. So this is the active power command from the plant controller to the inverter. So this is another good reason to keep an eye on these signals here. And test 14 is the weak system test here. So we're stepping, is it? Yes, it is. Yeah, so the first fault and recovery is okay. And on the next one, it's no longer okay. So I think on the second one is, have a quick look. Short circuit ratio on the first one goes from 5 to 2.5, so that's fine. And then 2.5 to 2 is a problem for this inverter. So, if we knew that the system strength was 2.5 or below 2.5, let's say, then this test might might inform us that we need to do some tuning on this model to get it to work in the final system. Okay, so the next, so yeah, any questions on these tests so far? Good, everybody still with me? Great. Okay. So the next thing I'll show is a brief workshop on a couple detuned models, and we can. I'll need your help to diagnose what is going wrong with these models. So get ready, help here, and the test that we're applying here is I added another test 15 here, where I'm just stepping from SCR of 5 to SCR of 2.5 with a fault and then clearing the fault. So it's just the first part of this sequence here. And what I've done is I've taken this model and I've detuned it 3 different ways. And so yeah, we can have a look at what the issues that we're seeing and maybe talk a little bit about what can be done to fix it. So the first test here, and this is my detuned model A, let's say. I don't have any results for it, of course. Let me just run it again. All right, so I had a fault and my IBR plant recovered, but I'm seeing something happening here. I changed one number in my model to make this happen. Anybody have some ideas on where we should look? It is, each division is 5 seconds here. I can put the grid on. So it's pretty low frequency. I think less than a hertz oscillation here. Any ideas on where or what we should look at?
Whether it's a communication delay or tuning out the controller.
Let's have a look. So if we look at the plant controller signals, we can look at the Q command out. And if we take this Q command, let's just take this graph. Here and just compare the command. Actually, this is the command at the inverter. So it's actually going to be matching, but what we actually want to see is the command here before the sampling and this time delay. If we were to plot it here, you could see that it would be basically out of phase or relatively out of phase with the oscillation on the system. So the detuning here, I think the PBC is exactly the right place to look for this. Main reason being that it's basically the frequency of the oscillation is going to be our main indicator there, that it's in this couple of hertz to less than a hertz range. It's a good indicator that it's related to the plant controller. And so the detuning here is, all I did is I took these pure communication blocks and I increased them. They were previously, I think, 150 milliseconds communication delay, and I bumped that up to 500. And that's enough of a difference to get this type of response here, right? So this is, it's totally stable at SCR of 5, no oscillations at all. And then we change our grid strength down to 2.5. And when we change our grid strength, we need to remember that the grid voltage is going to get a lot more sensitive for a given Q injection. So now when the plant controller tries to ask for a certain amount of Q out of the inverter for a given step in Q, it's getting much more voltage. So the system strength is like effectively a gain on this voltage control loop inside the plant controller. And the amount of gain compared to the phase lag in the loop was too high in this scenario. So we can we can make these plant controllers relatively fast and get fast response times. We have to be very considerate about the amount of phase lag that's in the system. We can very easily tune them to be too aggressive for a certain strength, for a certain system strength, and for a certain phase lag that's in the control loop. So this is one aspect that we need to think about, especially when it comes to very weak systems, in that we have this system strength acting as effectively a gain on the voltage control loop. Yep.
Planner, right? And so I'm just wondering, so if we have a weak part of the system and then we're building a new line out to it, generators out there tuned to the low CR, we may need to work with those guys to adjust the settings potentially.
If you're adding, I mean, if you're strengthening.
Yeah, afterwards.
Yeah.
To do a system, basically.
Yeah,
think
I
is
mean,
what I heard you say.
So if they were tuned to be stable in a weak system,
Yeah.
and then you make the system stronger, they're still going to be stable. They're just going to be slower. Yeah.
Okay. Still work with them.
Yeah. You basically have turned down the gain on those voltage controllers.
Like you theoretically could restudy and retune them to optimize, to get faster, bigger Q response if you wanted to, or you needed it afterwards. But you don't have to. And it's much less dangerous, not dangerous, but risky, I guess, to do it that way than the other way. It's much different when you're connected to a strong system and that system gets weaker over time. Because then you're going to start seeing these types of things. Going the other way around. It's really up to you and your appetite for really optimizing that response. If you had a really tight system, you might want to optimize it. You always just note it and keep it in mind for the future. If you need a little extra something, well, I know this one's tuned slowly. I can maybe tune it back to whatever in the future.
And of course, the other danger is that you tune them for the strong system, and now you lose that line, and then system's weak again. That causes a problem.
That piece is very important too. Is like, it's not just system intact for when you're considering system strength. Is the lowest system strength, the weakest system strength for the worst contingency is really what you should be tuned for. Because the example we saw yesterday was there's just two contingencies that caused that low SCR. The other time it was 10x stronger. So something to keep in mind when you're trying to determine if it's weak or not. It's both, is it weak in the real system intact in the serial mission planning world, or is it weak in the N-1 -1?
So for this one, we could fix this in a number of different ways. One would be just to detune the voltage control loop, just turn down the gains, and that would make this go away. So just slug the voltage control loop is going to help a lot here. The downside, of course, is now that you have, you might have slow voltage control now. Maybe it's too slow. Maybe it doesn't meet requirements, or maybe it causes an issue on the system. And the other possibility is you could try to figure out whether this communication delay can be decreased. There's some tricks you can play. Let's say, as far as I know, I haven't done this, but I hear you can do things with Modbus that make it faster. So check that you're sending only what needs to be sent for these very fast control responses, and that you're not like sending a whole bunch of other random information that could be sent on a much slower timescale between the PBC and the inverter. Maybe you need to upgrade some metering equipment or something like that. So, anyways, haven't ever set up a plant controller in the field, so it's out of my wheelhouse. But I understand there are things you could do to reduce this time. The PBC vendors could speak a lot more to that, but.
Some inverters, if you hit them too quickly with community requests. So you have to find that middle ground of, okay, how can we do it with engineering margin where they're still going to be okay.
So a lot of times you just have to work with you know, the systems that are
And then
there.
you have to detune your PIDs or a PID rate limiter.
Right, yeah, rate limits for sure. Fantastic. Okay, I got two more for you all. Scenario B here. So again, I've detuned this controller in a different way. Let me put the time axis on here. Red, you can see each division is, now we're looking much closer. Each division is 250 milliseconds here. So this is a much higher frequency oscillation. Pretty heavily focused on in reactive power here, but definitely visible in active as well. Any ideas on what's going on in this case? Where can we look to find the problem? Inner loop. All right. Good. Good guess. Yeah, that's right. So what I did here to detune this model is I just took the inside my IBR. I just went ahead and increased the find my control block here. Oh, actually, that's an up page. Sorry. Yeah, in the inverter control section, I just increased I think I just decreased the time constant on the reactive power control inside the inverter, which gave us this really nice weak system instability happening here. So this is kind of just classical inner, like this isn't actually the inner control loop. It's actually just before the inner control loop. It's just the active power regulator that sits just ahead of the inner control loops. But you could make this sort of thing happen by playing with any set of those gains. So it has to be tuned very carefully, let's say, to get a stable result in these weak systems. And you could take any of these controllers in the loop, and if they're tuned poorly, you could create an instability like this. And this is all just induced from a higher a lower system strength. So how do we fix this? Any thoughts on how we, if you saw this happen, you didn't know why it was happening, you had an idea it was at the inverter, what's your next step? Say as the utility evaluating the model.
Numbers from it?
Yeah. If you have some other information about what the parameters should be, or can tell whether they're reasonable or not, that's one thing. Probably those inner and semi-inner gains are often not accessible to users, so you might not even be able to tell what is going wrong. If we see something like this and we know that the system strength in the system is going to be at or below what we're testing here, we would probably just send it back right away. And you can play around with it to figure out why it's doing what it's doing, but this is going to be very much in the domain of the manufacturer to tune this out of the inverter.
Just to underscore it, just send it back. That's the easiest piece of advice, especially for system operators, right? We probably don't have access to them. If you do have access to them, you probably don't know what they all do, because those are inner loop parameters that are very sensitive and very important for IP, because they're not important to IP, but you can use them to get information that you shouldn't have, right? So that's the reason why they're not there. And also this is not something that I would look and see and say, oh, I can tune this out of it. This is like very clearly you change the parameter, but it's very clearly an issue with a time constant or a delay or something, or a gain that's completely wrong. So this is not something that even if it's a developer who has a contract with the manufacturer who has a modeling staff, it's probably even not their responsibility to do this. But like Lucas said, if you really want to, and like what I used to do, when I was curious and had time on my hands to do that, was like, I would take a look and see if I could figure it out. And then I'd say, hey, I think it's this thing, while I'm sending it back to the manufacturer. So there's a middle ground too. If you want to learn from these, you can, but ultimately it's up to them to change it. And also, if we're just warning for some folks who are system operators who don't do this or who may do this, is once you change something, like if you go in here and you've seen it before and you know it's a time constant, I change a time constant and say it's a generic model because I know what it does and what it means, and I get it to work, then it's not the plant model I was given. So that's another reason not to fix it yourself. I mean, you can fix it yourself, but just send it back for confirmation. But if you're busy, like we all are, especially in the planning world, in the interconnection processes where these tests are happening, or in a time crunched area, just give it to the manufacturer. They'll figure it out in an hour versus how long it takes to look into something you've never seen before. So
Yeah, and I would even, depending on the situation, but be careful about giving leading advice to the developer and the manufacturer. Be careful of, even if you know very well what's going wrong and you have a very clear idea of it, like you saying, oh, you probably need to tune this specific parameter. It's like, they might take that, okay, this is the only thing I can do now because the utility won't let me connect unless I tune this specific parameter. But don't be scared to sort of like play dumb a little bit and say, I found this issue, please tune it. It's not a bad idea to just stay a little bit vague about it, even if you know exactly what's happening under the hood. This allows you to not take responsibility for the change, right? So it's very much, you don't want to take responsibility for changing something and then have something after the fact go wrong with this change, and they can track of it all the way back to the utility engineer who told them to change this one gain or whatever, right? So just leave it in the OEM's hands whenever possible, if it's a very sensitive parameter like what we're seeing here. It's a bit of a different story when we're talking like voltage troop values in a plant controller or something like that. That's a little bit different, but this is sort of very much in the guts.
a good general rule is it's in the plant controller. You can probably tune it, just really generally. If it's something in the inverter level, you probably want to ask confirmation. Even if it's like really clearly labeled inverter level voltage ride through gain and know exactly what it is, you probably still want to confirm with the manufacturer because that gain could have effects on other capabilities and stuff. And also the thresholds. People love to change the threshold for ride through, especially in ERCOT, right? Because in ERCOT, if I make the high voltage ride through threshold 1.4 per unit, that I'm never going to hit it, I'm going to have a beautiful, perfect ERCOT response. I'm going to have a perfect straight line down, maximum Q, active power is going to be 100% perfect. But that's not something that probably you're going to want to change the product. And it's definitely not going to get past the manufacturer when they have to go put it. There's a lot of reasons not to change things unilaterally.
And just one more to add on to there is like if you do go to the route of like, okay, you sent it out, get them to fix it, but also try playing with it and try to figure out what's going on. Just like be ultra cautious to like, save a separate copy of that file so you don't accidentally send someone the modified case that you were playing around with, right? Like you might think.
Sounds like a personal experience story.
Well,
we've all done it.
We've all been there. Some practical note.
What if you're here are defining the 2800 standard?
I mean, this test specifically is not defined in 2800. Like, so like in the presentation here where I was going through these various tests here, the tables here are sorry, some of these tables here are from the standard. The standard is, it's giving some performance requirements for frequency response, and it's giving us ride through envelopes for voltage and things like that. It's not 2800 doesn't tell us what tests need to be run like at all. It doesn't give us any insight at all. 2800.2 is what we look at to help inform us on what basically how to verify some of the aspects of 2800 in at a plant level. So these tests here, these are not, to be clear, these are not what's in 2800.2. 2800.2 is like near done. I probably could have shown it and given a very similar presentation in that way. These tests that I'm showing here, these are coming from the electronics model requirements, which are not in any sort of standard, but the 2800.2 test, which will be become official soon, they're pretty similarly aligned to what I'm presenting here. And
The background and why I asked you to come in to give this presentation for these tests is part of the fact that I was in leadership for SG3 and for .2, 2800.2, and this, what's presented test procedures were the starting point that we used when we had the discussion what tests are done. So this is the full list of test procedures, or not, this isn't the full list, but this is the selected from the full document that we all use, and I believe it's public anyway, right? And it's public, and it was the starting point for 2800.2. And then some tests got removed because I don't like to do all the tests, and that for a bunch of reasons, tests got removed. So the public document for these is more than you have in .2, but .2 is what we got for content. That basically just means a lot of tests came out. But I'm pretty sure that the tests that made it in 2.2 are near identical in procedure and performance criteria. So this is really solid overlap. But the reason why you're here, I mean, you're great at it, but why I wanted this section is with this document is it was the starting point for 2800. And I think it's good to see the starting point before the standardization process too, because then you kind of get a feel for how standardization works. You're always starting from some technical place, and then we all talk about it, and then we agree on something less technical. But there is, like you said, there's very significant overlap between what's going to be published in .2 in the spring and this public doc.
so one more detuned example here, and then I think probably we'll break. So this detailed model C here, this is again the same fault, except after the fault here, if we look at the active power out of our plant, it's not recovering. So this active power is going to zero. So it definitely looks like that the plant has tripped for this event. And we can go in and look at again, similar sort of thing as what I showed before. You can go into the IVR model in this case and have a look at the flags. And you can see this OV2 is the one that went for us. And you can check the protection setting again. And OV2, that's the change I made in this example. The detuning I did was just to kind of mess with this voltage threshold. I made it, I think it was 1.1 for 20 seconds. I made it 1.15 for 4 milliseconds basically here. And that resulted in a trip. So nothing sort of like too interesting there, but in terms of like, again, how would you go about fixing this? Very similar to sort of thing as to what we said with the intercurrent and with the active power control loop there. You can look at this and say, okay, this is like a very restrictive trip threshold for 1.15 for like a quarter cycle or whatever this is like probably the actual equipment should have greater ride through than this. And but you would basically highlight this as a trip in your model testing report and try and get them to fix it. This is, you might have a good hunch that the equipment capability it can handle more than what you read here. So it should be a pretty easy one for them to correct. Just increasing the setting, assuming that the capability is beyond this. So Okay, so there's three examples, a brief workshop on a couple things you might see in model testing. I'll say, I think I have a little bit, yeah, just a couple more notes on how we can make this basic component even better. It's not that hard to do. It's not that good right now, to be honest. But one thing we could do is right now we just have our voltage magnitude on the source side of the impedance is just fixed at like 1 per unit. We're not doing any sort of back calculation or anything like that. So that means we are not able to get like a very precise P, Q, and V at the POI because of that. So we could add some back calculation to figure out the source voltage angle. Similarly, we can figure out what voltage reference we need to set to the plant controller to get a certain POI voltage and reactive power out of the plant. So these are two things that you can use to get you to Qmax, Qmin. You're going to have to do this if you want to test things like Qmax, Qmin, basically. And the other thing that I don't have here is, an actual plant has a tap controller, or not all plants, but some plants do. If the plant has one, you might put in a plant controller or a tap changer into the model, and you might make it artificially fast to get you to a reasonable starting place quite quickly. You're applying your test at 5 seconds. Maybe you say for the first 4 seconds, tap controller, just go crazy. Just get me, get the inner voltages to the right, band, whether it's 2% or whatever your dead bands are. And then after that, just stay put, just like don't move anymore, just freeze. If you have a load flow solution available inside your EMT tool, then you don't really have to do this. You can just solve your load flow and set the tap based on a load flow as well. That's an option if that sort of is in your workflow. It doesn't really in ours, but it could be in yours. And then you can have standardized and detailed plotting. So, a specific set of terminal and POI voltages that are plotted the same for every model test that you run. You could look at sequence components, harmonic components. And then the last one here is you could wrap this test component in some dedicated external automation. So right now I use the inbuilt sort of batch run process that's inside PSCAD to run these. You maybe want to have, you could definitely develop a more sophisticated tool that batches these in a different way. That might include some automated plotting, automated post-processing. You could look at, whether things trip, whether they have oscillations. You could program some post-processing there using Python or whatever to process the signals and put them into some sort of Excel sheet for you. And you could.
One note real quick, there are some other EMT tools do have a test bench and automated process in there already. So just something to keep in mind when you're looking to pick a tool is that, you may do something manual, some other tools will have that test bench in there already, and just keep those in mind for your needs, what you want to do.
Yep, and there's some open source, I think there are open source tools out there as well that automate some of this process out there. If you look around online, you might get some help that way. Like ERCOT, their tool, I think I'm not sure if anything is black box there, but NIAC Corporation has a kind of a module as well. There's a few others that have like more sort of commercial products as well that you can purchase that do some of this, possibly all of this in a lot better way than what I've shown here. But whatever route you end up using, you should, don't use anything blindly, even if you paid for like a very nice commercial tool to do this for you. Do your due diligence to understand what the tool is doing for all of these tests. You don't want to it's your responsibility at the end of the day. It's not the person who made the tool for you. So, okay, I think we'll break now for